Hello, and welcome back to Technology Now, a weekly show from Hewlett Packard Enterprise where we take what's happening in the world and explore how it's changing the way organizations are using technology. We're your hosts, Aubrey Lovell
and Michael Bird. And in this week's episode, we are answering a very simple question. How do you build the world's fastest supercomputer? We will find out what makes a supercomputer, a supercomputer. We'll be exploring the different building blocks of a supercomputer. And we'll be asking, is there a limit to how big these machines can get?
That is correct. So if you're the kind of person who needs to know why what's going on in the world matters to your organization, this podcast is for you. And if you haven't yet, subscribe to your podcast app of choice so you don't miss out. All right, Michael, let's get into it.
Yeah, let's do it. Right, so Aubrey, I think we can all agree that computers are one of the marvels of modern technology.
Absolutely. Can't imagine a life without them.
Yeah, I mean, we carry them in our pockets. I'm pretty sure they're embedded into pretty much everything we interact with.
They're even in fridges now.
I've seen a fridge that has cameras in it and it can tell you when stuff is gone.
Yeah.
Anyway, the amount of stuff we can do on them is really quite remarkable. But what happens when your standard laptop or even your company's server room isn't enough? Well, you need to scale it up.
Enter the supercomputer. Now, these titans of engineering perform tasks, models, and simulations of some of the most complicated processes in our universe, covering everything from weather to atomic physics and even discovering new drugs. And currently, the world's fastest supercomputer, Capitan, is housed at Lawrence Livermore National Laboratory, where it was created in collaboration with the U.S. Department of Energy and the National Nuclear Security Administration to ensure the safety and security of the United States nuclear arsenal, among other things.
Now, the world's most powerful supercomputer is obviously a huge topic. So to give it the respect it deserves, we've split this topic across 2 episodes. This week, we are going to look at the process of building the world's largest supercomputer. Next week, we're going to explore what you can actually do with it.
That's right, Michael. And to kick us off on this topic, we are thrilled to be joined by Bronis de Supinski, the CTO of Livermore Computing at Lawrence Livermore National Laboratory.
Bronis, welcome to the show. So first question, in 1 minute, what makes something a supercomputer?
Well, a supercomputer is really just a computer that has more capability than the vast majority of other computers available at that time. What's a supercomputer today, 10 years from now, might be sitting in your pocket. That's happened quite a bit of times with computers that I've worked on during my career. Now they sit in my pocket.
Wait, so you've worked on what at the time you called a supercomputer, but nowadays is just as powerful as a smartphone that I have in my pocket.
That's right.
Wow.
That's the way technology has gone.
So by the definition of a supercomputer today, how does it differ from the laptop sat on my desk or a server, racked in a server room?
It depends on the supercomputer. So sometimes the technology can be very different, but oftentimes it's just very similar technology, but a lot more of it. The individual nodes of a supercomputer are very similar to the computers in your laptop or your desktop system, but there's a lot of them.
Yeah. Okay. Well, I'm going to come on to that later because I really want to ask you about the details of that. But can you sort of explain how do you measure the size of a supercomputer?
The most frequent measurement that we use to rank supercomputers is performance on a benchmark called LINPACK, or High Performance LINPACK, HPL. And that basically is solving a system of linear equations and how large of a system can you solve in how much time. And so that then translates to a number of floating point operations per second that can be achieved.
And so El Capitan, what's the flops number?
What we report is peak, so the guaranteed not to exceed performance is 2.74 exaflops. So that's 10 to the 18th flops. What it got on LINPACK was 1.79 exaflops. So it actually was doing a somewhat useful computation at a rate of almost 2 exaflops. You'd need more than 1 million of your smartphones to be able to do that computation and to perform computation at that same rate. The thing is that then they also, because it's solving a single problem, they have to be able to communicate and work on that problem together. So you wouldn't be able to get 1 million smartphones to compute at that rate because they don't have the ability to communicate quickly enough.
So does that mean that El Capitan is an exascale computer? And if that's the case, what does an exascale computer mean?
So El Capitan is certainly an exascale computer by pretty much all of the metrics one might talk about in terms of scale. Of its 10 to the 18th is kind of dominates throughout. So for us, because we're focused primarily on modeling and simulation, we're very concerned with being able to do double precision floating point operations. So that's 64-bit floating point operations. Our application teams need that level of precision to get accurate answers. And so when I said the 2.74 peak, that's double precision floating point operations.
So I imagine you can't just pick up the phone or hop online and just quickly order yourself an El Capitan. I suspect it's quite a complicated process. So I wonder if I could just ask you about how do you go about building a supercomputer? What's the first thing you need to do when you're setting out to build the world's fastest supercomputer?
If you are looking at doing something in a cost-effective way, really managing your money well, then you need to work with the technology providers, so the system integrators, the processor manufacturers, understand what they can do and work with them closely to figure out several years in advance how we can push the envelope. Because it really is about building something beyond what anyone else is able to build at that time. And so that takes time, it takes investment. Also, it takes a lot of close work looking at here's the problems we want to solve, and here's the ways that we could evolve technology to solve them better. The U.S. Exascale program actually took place over more than a decade, really.
So in terms of the environment for where the supercomputer lives, like what are the facility needs? Like, is it a big air-conditioned building? Does it need to be close to a power station?
I think our site is kind of a good example of what you need nonetheless, right? So first of all, Lawrence Livermore is just across the road, literally. We have a very large substation from one of the two main power providers in California. And also not very far away is another substation for the other big electricity provider. So our site happens to be very well located in that we have access to very large amounts of power. And the amount of power you need to run a supercomputer is large, and it keeps getting larger. But then you need a whole bunch of infrastructure to bring that power from the distribution point at your site actually into the building where you're going to have the system. Prior to El Capitan, our center had capability to deliver 45 megawatts to our main computer and floor. We actually run our center so that we are able to have the current system still running while we're fielding and deploying the new system. All right, so that means we actually want to be able to run two very large systems at the same time. In addition, you need to be able to cool the computer. So when you're using a lot of electricity, moving all those electrons generates a lot of heat. So our building was originally designed to house air-cooled systems, but we also had the ability to do water-cooled. So that sits just outside of our building, is the ability to take all of that electricity and bring it into the building. And we have 6 very large cooling towers that we added for the extra cooling capability. Then you have to have all the infrastructure to bring it into the building and then distribute it to the actual computer, which occupies a fairly large amount of floor space in and of itself.
And so if El Capitan is water cooled, does that mean it's, from a power and energy perspective, is it more efficient?
Yes, it's actually a lot more efficient, because that means that we can run the clocks at higher speeds and much more efficiently remove that heat.
Thanks so much, Bronis. It's always nice to see previous Technology Now topics like liquid cooling come up so we can actually see them in practice. And I also want to quickly define something which we just heard from Michael and Bronis. We measure the speed of supercomputing in flops, which is floating point operations per second for the uninitiated, but we didn't ask what a floating point operation is. So luckily, the answer is relatively simple. Floating point operations are a type of math that use floating point numbers, which can be thought of as just a different way to write the numbers that we use. Anyway, looking forward to hearing more about how we build a supercomputer later in the show.
Okay, so now it is time for Today I Learned, the part of the show where we take a look at something happening in the world that we think you should know about. Aubrey, what have you got for us this week?
So I assume you've seen films where people use infrared cameras, right, Michael?
Yeah, to sort of see through things.
A lot of like military high impact movies, that you see them using this type of technology, right?
Yeah. Or I've seen those sort of, I think you call them a cop show, where they're following somebody in a helicopter at night and they're sort of hiding in a woods and they use infrared cameras to find them.
Well, in a paper published in the journal Cell, researchers in China have announced the creation of contact lenses which respond to infrared light, turning it into visible light.
Wow.
And allowing the wearer to see something which would have previously been invisible. That's incredible. And I also wear contact lenses, so this is very exciting for me. But I also am like, the amount of power you could have to like be able to see in the dark. I'm already blind. So like to be able to have that in the middle of the night would be crazy. Unlike current night vision goggles, which are bulky and kind of require power, the new contact lenses are easily wearable and do not require any external power source. However, these changes do come with a couple of setbacks. I knew that there was a catch here.
There's always a catch.
The lenses do not provide any sort of detailed vision yet, as they only respond to high-intensity infrared light. However, the researchers note that even this could be useful for sending discrete messages in security, search and rescue, and military scenarios. Very interesting. Obviously, like any wearable tech, there are a few safety concerns. The contact lenses work by using nanoparticles to convert the infrared into visible light, and there are worries about these leaking into the eyes.
Okay.
However, they still mark a step forward towards what could be an exciting new technology.
That is exciting. I'm sort of following some photographers who have been taking off filters from their cameras so they can shoot in infrared, and everything looks a bit sort of interesting looking. I imagine that'd be quite cool. The world would look very, very different with everything in infrared. Do you think you could turn your TV on and off just by sort of blinking? That'd be quite fun, wouldn't it?
That would be next level. But I will say that last paragraph kind of got me like, I might want to be a late adopter to this because I don't want any type of infrared leaking into my eyes. So no, thank you.
The nanoparticles is maybe what I'm slightly worried about, leaking into my eyes. But anyway. Right then, now it is time to return to our guest Bronis to find out exactly what sort of kit we need to build a supercomputer like El Capitan. So what sort of hardware do you need for a supercomputer? I mean, is it the same sort of traditional hardware that you would have, as a standard server sat in a rack? Storage, networking, compute, memory, or are there some additional components that make El Capitan special?
Well, there are some components that make it special, but at the very most basic level, there are processors and there are solid state drives, there's hard disks. The file system actually is still air cooled. So there's fans on that. There's something that you don't have in your laptop or your desktop is we have cooling distribution units that move the liquid through the cabinets. So that's a little bit unusual. The processors in El Capitan are somewhat special. In most supercomputers, we just have faster CPUs and GPUs than you have. El Capitan has something that's called an APU, which is an accelerated processing unit. And that's a single device that actually brings together CPU cores and GPU cores. The MI300A is the first server class APU. So that's pretty special. The device we have that houses our SSDs is a bit special in that it allows the SSDs to be directly mounted by multiple compute nodes, which is kind of unusual. But in the end, it's a large amount of processors and storage devices, and they're not that different at some level. They're higher speed, higher density, higher quality.
I mean, how many processors, GPUs, SSD, like how many are we talking? Hundreds, thousands?
So supercomputers today typically have multiple what we would call compute nodes. So El Capitan has a little over 11,000, so 11,136 compute nodes. And each of those compute nodes has 4 APUs. So there's 44,544 APUs in El Capitan. So that's a fairly large number of processors in one system.
So does a supercomputer just sort of run off-the-shelf software? Does it run like a normal desktop operating system? Or is it something a bit more specialized?
El Capitan uses what we call the Trilab operating system software, or TOS. but that's just built on a standard Linux distribution. Now, we do some things where we remove a lot of things that you don't need. So it's running many fewer daemons. The compilers that we use are built largely on open source compiler infrastructures. There are proprietary ones also, but that's what we use to generate the machine code for the applications that we run. The applications that we run are typically, homegrown applications. There are ISVs that have applications that run also, but those are not so much ordinary applications typically because they have to be programmed to be able to run across a large number of processors.
So the sort of software and hardware come together. Presumably there's a period of testing it, making sure everything is connected correctly and is talking to each other correctly. Like, how long does that take?
With El Capitan, there were some things that led us to actually deploying all the cabinets and all the networking infrastructure. And then once we started installing the compute nodes, that took 2.5, 3 months, I think, because it takes a long time to actually like bring them in, slot them, bring them up, make sure that they're running correctly, that nothing got damaged in shipping. And then takes a bit more time to really make sure everything is running correctly and running well. Honestly, people will be a bit aghast, but it takes a really, really large system to get it up and running well. It takes almost a year.
So what would need to be done to be able to build a computer even bigger than El Capitan? I mean, is it as simple as just, if it was 11,000 nodes, you just buy 22,000 nodes? Or actually, are there some technical or even physics-based challenges that mean that it's not as simple as doing that?
You certainly eventually reach a point where it's not connected in the same way, right? Where the networking connections become kind of untenable. Doubling the size would primarily be a matter of money. I mean, there also is like supply chain issues, like getting all of that stuff manufactured is also very complicated, very time consuming. 10 times as much, there become more challenges involved in that. Being able to wire it together in the same tightly connected way becomes very difficult. Then, like all of the nodes in El Capitan are able to communicate with each other at fairly high bandwidth and low latency, so fairly quickly and at high data volumes. At some point, it becomes difficult to build a network that does that.
Well, Bronis, that has been utterly fascinating. Thank you so much for your time. And with the speed of progress in the tech world, I think it's particularly interesting to consider how long it takes to build these machines, as I imagine at some point we will start approaching like a maximum speed for supercomputers. So I guess, the pretty exciting questions start to arise. Where do we go from here and what's next?
Right then, we are getting towards the end of the show, which means it is time for This Week in History. Aubrey, remind me of last week's clue.
Okay, so the clue last week was it's 1943, and this patent had just been granted for something that almost every single one of us uses daily.
Oh, yeah, and we were talking about whether it was an appliance or something. I think I said refrigerator. I think you said microwave.
Yes, and in this case, we were going in completely in the wrong direction because we should have been thinking much, much smaller. And I don't think that helps me at all. I have no idea.
Right, what is it?
Okay, so I need you to do something. On your last hint, I need you to write this down for me. You ready?
Right.
So write down technology now. And once you've done that, I want you to look in your hand. And what are you holding?
A piece of paper?
So this is actually the story of the biro, which is a ballpoint pen.
My other hand.
Your other hand, sorry, I was not clear.
You're
just probably looking at a blank hand like, what are you doing? No. In 1943, the first successful ballpoint pen was created by a pair of Hungarian brothers, Laszlo and Jerzy Biro, and initially their invention was patented in Britain before the advent of World War II. However, the brothers were forced to flee Hungary to Argentina to avoid persecution, so the pen itself was not marketed until 1943, after they were granted an Argentinian patent. So Laszlo had wanted to create a pen which had fast-drying ink and didn't smudge, unlike the fountain pens used at the time. And working with his brother, they created a thick, viscous ink which paired with the ballpoint of the pen to create the pen we all know and use today. I do want to give you a little credit for one of those things you mentioned last week, Michael, because you did say something about the space race. Now, there's a myth that the biro was created as part of the space race, which is sadly untrue. However, NASA did transition to what was known as Space Pen in the late 60s, which was a pressurized ballpoint pen, which could be used in zero gravity, which is pretty cool.
I remember going to one of those shops in London that has like sort of sellers everywhere that would sell the newfangled thing. I remember selling the Space Pen, and you could buy the Space Pen, and everyone was like, oh, the Space Pen. But most people use the pen normally.
Right? It's not like you could actually test it out, which would be cool if you could. But what do you have for us next week, Michael?
Okay, next week. It's 1963, and this 26-year-old cosmonaut is about to set an off-world record.
Ooh.
Cosmonaut's the clue. So it'll be like a USSR. Yeah, I'm going to say maybe Yuri Gagarin goes to space, but I think that was probably the 50s. I've probably got that wrong.
Well, I'm going to double that because I have no idea who it is, so I trust you, Bird. Okay, that brings us to the end of Technology Now for this week. Thank you so much to our guest, Bronis, and of course to our listeners. Thank you so much for joining us. And if you've enjoyed this episode, please do let us know. Rate and review us whenever you listen to our episodes. And if you want to get in contact with us, please send us an email to technologynow@hpe.com. We would love to hear from you.
Technology Now is hosted by Aubrey, Lovell and myself, Michael Bird. And this episode was produced by Harry Lampert and Izzy Clark, with production support from Alicia Kempson-Taylor, Becky Bird, Paul Roisin, Alyssa Mitri, and Renee Edwards.
Our social editorial team is Rebecca Wissinger, Judy Ann Goldman, and Jacqueline Green. And our social media designers are Alejandra Garcia and Ambar Maldonado.
Technology Now is a Fresh Air production for Hewlett Packard Enterprise, and we will see you at the same time, the same place next week. Cheers.
Cheers.